Okay, lecture 2, high-dimensional probability for data science. Good. Let me share this though, sorry. Share. Got it. Share. Screen. Let me share this now. Oh. Okay. Sorry, let me do this one more time. Share screen. Start broadcast. Oh, here we go. Okay, lecture last time. So last class, we made a few observations. One, let me repeat them because they're the basis of this class. One, we actually live in a high-dimensional world. We are trained from the childhood to think that our world is three-dimensional, and that is correct. Our world is three-dimensional, but it depends on what we mean by the dimension. And that's a very narrow view, if you only think it's three-dimensional. Let me give you just one example in addition to all that we covered last time. So I was walking yesterday and there was this beautiful sunset, and the tree, there was a tree with a lot of leaves on it, and each leaf on this tree was trembling in the ocean breeze, and it was beautiful. And I was thinking, if you think of the velocity of each leaf, the movement, the velocity of each leaf as its own parameter, if you record that, so the velocities of each leaves, and you record it as a vector, let's say v1 for a velocity of leaf 1, velocity of leaf 2, and so on and so forth, velocity of leaf n, and how many leaves there are, I don't know, maybe 5,000, something like this, 5,000 leaves in the tree. If you record these velocities, that'll be a vector in a high-dimensional space in dimension 5,000. So even to understand what's going on with this tree, with the movement of this leaf, with the movement of this tree at this very moment, it requires us to consider spaces that are 5,000 dimensional, not three-dimensional, right? So this is a point in dimension n, where n is very high, and this space is maybe called the state space, the space that records the state of that tree. In this particular case, we just look at the velocities of the leaves. So the state space of a physical object, they're very, very high dimensional. In this case, it's 5-dimensional, but usually it's very, very high dimensional, the state space of our world. And so we actually live in high-dimensional world, although this tree physically inhabits the three-dimensional world. Even to describe what is going on with it requires us to move to high-dimensional spaces. So that was observation 1. Observation 2. The complexity of problems, of algorithms, becomes exponential in the dimension. And in this case, which is a bad news. Exponential, too large, it blows up with the dimension in a bad way. And to start with, we have dimension 5,000, so it's like 10 to the 5,000s, for example. Complexity is exponential in the dimension n, and we call this phenomenon the curse of dimensionality. And we illustrated this with an attempt to integrate the function in high dimensions, and that was exponential. Even to put the grid on the space would require exponentially many points, and so it doesn't work that way. However, and this is good news, probability, especially the new version of probability, if you will, high-dimensional probability, can help sometimes. And we illustrated this statement with Monte Carlo method of integration last time. And we will see much more. That we'll see much more examples where probability could help, and the idea of this course is to build your intuition of high-dimensional problems, high-dimensional spaces, and build your intuition about how probability can help with many tools that we have. So that was last class. Any questions? Good. Perfect. Okay, lecture 2. I will give you one more example before we go to the kind of the essence of this class. Next time, I will give you one more example how probability can help, and this will be one more example on how probability can help in high dimensions, can lift the curse of high dimensionality. And this next example will be in computational geometry. Specifically in computational convex geometry. It's an area of geometry that works with convex sets, and I'm sure some of you know what convex sets are, right? You work with convexity a little bit, but let's recall. Nevertheless, many of you have not done this. So, definition: a set, let's say it's T in Rn, is called convex. Okay, guys, those who know what it is, what is it in Ukrainian? Convex.
Опукла множина.
Yeah, thank you. Опукла множина. Perfect, thank you. Is convex if whenever there are 2 points in that set, the interval that joins these 2 points also belongs to the same set. So if, let's make it formal, for any 2 points x and y in the set, the segment that we denote like this, xy, also belongs to this set. This is x, this is y, and we require the segment to belong to this set as well. Just like that. So, for example, I don't know, this thing is not convex. This is obviously not convex because if I take this for x and this for y, the interval falls outside or completely. The ellipsoid is convex. The ellipses are convex because if you take any 2 points x and y and join them, the interval will be in the set. So this is check mark, convex. What else? If you take 2 convex sets and you, for example, join them together like this, just take the union of 2 sets, not good, not convex, because this is x, this is y, outside, so bad situation. However, if you take 2 convex sets and intersect them like this, that will be convex. So unions are not good, intersections are good. Good, okay. Now, the way of transforming a non-convex set into a convex set, that's called taking the convex hull. So the convex hull, опукла, що? Опукла.
Оболонка.
Оболонка. Дякую. Дякую. Опукла оболонка. Of a set T, which we denote like this, conv of T, is just the smallest convex set that contains T. It's the smallest convex set that contains T. I think it exists. Yeah, it will be just the intersection of all the convex sets that contain T. That will be the smallest one, obviously. Geometrically, what it is. So we take. Okay, let me just put it in red. Okay, I'll show for these sets that we have that are non-convex. What is the convex hull? So that will be the convex hull. Everything that's inside it. So like this. That's a convex set. Convex hull of T. This one is convex, so its convex hull is itself, of course. This convex hull will be like this. Yeah, and this is convex again. More examples. If T is, let's say, 2-point set, A and B, like this. B 2 points, then obviously the convex hull of T, what's the smallest convex set that contains the 2 points? Well, it has to contain the interval between them. It has to have this, and that's already convex. So obviously this is just a segment that joins them. Else, if you have 3 points, let's say A, B, C, the convex hull is this. This is T is A, B, C. The convex hull is just a triangle with vertices A, B, C. One more example. Let's say if we have a map of Ukraine. Okay, never was good at drawing, but let me try. Okay, so it goes here, and then there's the Western Ukraine. And there is this funny thing around Odessa, like this. I know it. And then, of course, there's Crimea. So Ukraine. I was never good at drawing. Sorry. Okay. Okay, you got the idea. That was my best take at Ukraine. So if we have that, then the convex hull of Ukraine would be this, right? You just kind of go around Ukraine in this manner and do something like that. So if T is a map of Ukraine, then convex hull of T is this, is red thing. Also, if T was just a boundary of Ukraine, that would not change the convex hull, right? If we just do this line, the convex hull of it will be still the same. Okay, got it. Perfect. Any questions about this just definition of convexity? Good.
No, it's cool.
Cool,
Yes, for me, it's really cool.
Yeah, it's really cool. Yeah. This is one of the things that that somehow is one of the main concepts similar to linearity. For example, you study linearity a lot in linear algebra, and convexity is kind of the same importance as linearity, although it's less studied for some reason in convex. Okay, similar to linearity, just like you remember this linear combination, like yeah, okay. So similar to linearity, convexity comes with that thing as well. So if you have any point in the convex hull, and this is a fact, think of it as a lemma, any point in the convex hull can be represented as a linear combination, but a special one. The sum of lambda I, actually, yeah, lambda I, zi, with so linear combination of the points in T. Okay. And moreover, these weights, let's call them weights, lambda I are like proportions or percentages. So lambda i's are all non-negative, and they sum to 1. Think of them as percentages, like they sum to 100% or something.
So now we have to find this base point.
Yes and no. So I'm not saying that these ZIs are, I'm taking the smallest number of them, right? So it's really close to the base. So you're correct that it's very close to a basis expansion, right? But we never claimed that we want uniqueness in this representation. So we can throw in more ZIs. Let's say if T was a finite set, I can just throw all of the points in T in there, all ZIs. The more I throw the points, the easier it is to find the combination, right? Because I can, in the worst case, I can just put weights to 0 if I don't like a particular case. So yes, we should find them, but in this, for the sake of this definition, ZIs could be just the entire T, the entire set, if you like. Actually, let's not prove this. So prove it. Do it yourself. It's not a hard thing. But let me illustrate it on the example. So first of all, that nice expression is called a convex combination of Z. It is a linear combination, but a special one. It's like a linear combination, only the weights are you have an extra comfort for the weights. They're positive, they're not negative. They sum to 1 like percentages. Example. Let's say you take 4 points. Z1, Z2, Z3, and Z4. And let's consider the convex combination with equal weights, like 1/4 Z1 plus 1/4 Z2 plus 1/4 Z3 plus 1/4 Z4. So if all of these weights lambdaize, if we choose them the same, well, then guess what happens? Where will be the Z then?
In the center.
In the center, exactly. Just in the center. They come with equal weights. So the Z takes kind of the same strength from all these points and puts them right in the center. As opposed to, let's something else, maybe U. If you have U, let's change the weights a little bit. Let's make this a little larger weight, and then a little smaller here, and then a little smaller, a little smaller here. Note how I chose the weights so that they must sum to 1 always. So if you sum these weights 4, 3, 2, 1, they sum to. Okay. So where will U be? Well, it takes a lot of strength from Z1 and very little from Z4. So it will be closer to Z4. Sorry, it will be closer to Z1 than it will be to Z4, obviously, right? So it will kind of drag in that direction. Okay, so we're dragging it in this direction, and probably it will be something like here, I believe, like very close to Z1, less close to Z2, even less close to Z3, something like that. I don't know. And so on and so forth. Okay, now imagine you continue playing with this, with the strengths, with the weights, and you put all different weights. Then where can these points be that you can represent them the way? Well, you can put point here, you can put point in the middle, you can put it close to Z1, you can put close to Z2 and close to Z3 and everything in the middle. So if you vary these weights, then you can just cover the entire square. So by varying weights lambda, to the entire square. And that's why this will be the convex hull of this point set C1. C1, C2, 3, C4. That's an illustration for this fact. Okay, convex combination clear? Yeah. Perfect. And now the most interesting question. Convex combination does not place any restriction on the length, on how many points you have. So it could be a very, very long representation, unlike the basis expansion. Remember, the basis expansion in dimension n has always length n. Okay. Convex combination, we never put that restriction. So the question is, can we find the most economical representation, the most parsimonious representation, the shortest? What would be the shortest one? Can we make m equal n, for example, or something like that? And a little bit later, I will explain why that is an important question in computation, because in computation, you want the shortest possible representation of objects, the most economical ones. The classical theorem of Caratheodory answers that question. Caratheodory, Greek mathematician. Theorem. It answers this question. Any point in the convex hull of a set in Rn can be expressed as a convex combination of, at most, n+1 points from T. Very close to the basis expression, except in the basis expression you have n points, and here's n+1. And why is it n+1? It's kind of clear. If you have, let's say, 3 points. Actually, you know what? No, let's have 4 points. Like this. And if you choose, let's say, if we choose, I don't know, maybe this point. Well, it's in the convex hull of these 3. Right, so we can represent this point as a convex hull of these 3. And we can represent this point as a convex hull of these 3. So we are currently E2, and every point in the square, which is a convex hull of the vertices, is a convex combination of 3 points, 3 vertices. And that's why n+1 is needed. We're in dimension 2, we need 3 points. And it's clear that you cannot, that this is optimal, that you cannot lower n+1 any further.
Does this theorem apply that we choose our n+1 base points after we know a point that we want to express?
Oh yeah, that's a great question. So yeah, great question actually. So if you think of the analogy with the basis expression, you first choose the basis for the space, and that unique basis works for any point. You can represent any point using that basis. Right? This is not the same here. You first choose the point, and for that point, you look for its representation with n+1. It's just like this example, exactly. And that example illustrates this all. For one point, for the top point here, this one, you choose one set, one convex combination, these 3 points, and for the other point, this one, it's the other. So the basis actually changes. It is adaptive to the point that you represent. That's a great question.
Thanks.
You're welcome. Good. As an example, let me go back to this Ukraine example. Actually, let me grab it from here, copy, and paste here. So this is example A, example B. As an example, like a corollary, any point in Ukraine, for example, Kyiv, can be expressed as a convex combination of, well, we're in dimension 2, there's of 3 border points. So for this, to prove this theorem, through this corollary, we take T to be the border of Ukraine, and just apply Caratheodory theorem, right? Any point in Ukraine, which is convex hull, can be expressed as a convex combination. So for example, I don't know, let's check. I think Kyiv is good there. Let's see. Kyiv is it around here? I think it's around here. Yeah. And so, yeah, so it could be expressed as, this is one border point, this is another border point, somewhere here. Maybe just the tip of Crimea, it's another border point. So for Kyiv, there are three points, maybe one in Sumy Oblast and one in Crimea. And for other towns, or for other cities, there are other 3 points, but there's always 3 points.
May I ask a question?
Yeah, go ahead.
Is it right that in case of this border of Ukraine, always 2 points will be enough, since we can just like draw a straight line through any point inside, and these intersections of this line with border will like do what we want from them. So like for any point we have always 2 bases with 2 points. Yeah.
Yeah, I think I understand what you mean. So for example, if you have this point, right? This point, you're suggesting something like that, right?
Yeah, so
like that. Well, as you see, this point is not necessary. This point is not on the border of Ukraine. It's in the convex. Well, by the border of Ukraine, I mean actually border of Ukraine, like this.
yeah, but if we take point inside, it will intersect the border.
Yeah, you're right. Yeah, that's a good idea. Okay, yeah, we can just then contract these 2 points until they hit the border. Yeah, so there's okay. Yeah, you're right. I just wanted, the moment I wanted to say that n+1 is unimprovable, you managed to improve it, because now we have 2 points and not 3 that we can do it with. You're right. So we can do it with 2 points. In fact, I think for any, yeah, that would be true. Probably that would be true for any curve, any one-dimensional curve. So if we start with one-dimensional curve and
A
take
closed curve.
What's that?
A closed curve.
A closed curve. Yes, we take a closed curve, and then we take any point in the interior that closes the curve. Then we can find 2 points. So that actually is an improvement for n+2. Yeah, which kind of counters my point. So you're right. However, if we take a set that's not a closed curve, let's say a discrete set of points, then let's say, if instead of Ukraine, I took something like this, and took, let's say, this point, then you can only, again, a bad example, I guess, this point. That doesn't lie on any segment, then 3 points are required, I think, to represent it. Okay, that's actually a great observation that you made. Thank you.
May I ask the question also?
Yes, Maxim.
For the Ukraine, for example, if we choose the point in outside of Ukraine, but in the convex hull, then it's also it can also be represented as 2 points, right? At least it looks like that.
No, I didn't see that. If we take, let's say, this point. Okay, yeah, this point is good.
If we consider the Ukraine to be a closed,
yeah, let's say closed curve. Yeah, closed curve.
yeah, closed. For open, it shouldn't be true, but
yeah, it should open. Yeah. I think it looks so. What do you guys think? It's true, right? Every point I take inside this red region, inside the convex hull, can still be represented as, let me draw this, can still be represented as a convex hull, like an interval of 2 points on the border of Ukraine. Anything like this, for example. Anywhere I take it, that's true. Interesting. Okay, that's a nice theorem to prove, actually. Yeah, try to prove it yourself. So you take any closed curve, you take the convex hull of it, and the theorem is that for any point in the convex hull can be expressed, any point lies on the interval whose endpoints are on the curve. Yeah, cool observation too. Great. Okay, I'm glad you're making them. Very good. Any other notes, observations, questions, objections? Good. Okay, so the game, the significance of which I will tell a little bit later, the game is to lower the number of points that represent X. So again, the definition of convex hull does not require any bound on the length here, but we would like to have the most economical representation. The most economical representation is attained by Caratheodory theorem. It says that you can always take m less than or equal to n plus 1, and that is unimprovable. Okay, this is state of art. This was the state of art before 1970, actually. And now there is a cool theorem that probably you will not know. If we allow not to exactly express z, but approximately, if we allow a little bit of an error here, I don't know, 1 millionth of an error between z and this. So if you allow approximate representations here, then not only we can improve n plus 1 down, but we can find representation with constant number of terms that is totally independent of dimension. An amazing result. So this is called Approximate Caratheodory theorem. Approximate Caratheodory theorem. We take any set. Well, because we're talking about errors now, let's find the correct scale. So let's scale t, so the diameter of t is at most 1. The distance between any 2 points of t is at most 1. That's just a scaling thing. Then any point in its convex hull, if you give me a budget of k points, so for any k, So you're like, you're giving me the order. You say, okay, here you give me point X, and you say, please represent it by K points in the convex hull. Then this is how I can do this. So there exists, I will give you the points in T, K of them, such that the error between, okay, sorry. So that, okay, there's lots of good news here. So I can represent X as a convex combination. Moreover, I can represent X as a convex combination with the same weights. Crazy. Same weights. So the way all of them needs to sum to 1. So they should be 1 over K each. And the error, which I measure just in the usual distance, I will denote it with the norm 2. That's a usual distance in Rn, is less than 1 over root of 2k. Don't pay attention to number 2 yet, but the idea is that this thing goes to 0 as k goes to infinity. So the error gets better as the more points I have, the better I can represent. That's kind of obvious. What is surprising here is that the error does not, nothing depends on the dimension here. So if we want the error to be less than, let's say, epsilon, we equate the right-hand side with that, solve it for k, and this is how many terms I need for that. And this is dimension free. It does not depend on the dimension or the geometry of T. There is no n anywhere anymore. We'll prove it in a second, but let me ask you, are there any questions there? Okay, so here's the plan. First prove it, then next time I will maybe we'll spend maybe 2/3 of a class explaining different applications to data science of this theorem. But as of now, what should be clear how this is relevant to something is that we're trying to express X using a given dictionary, kind of. And we need very few words in that dictionary. If we're set error epsilon, then the dictionary is very short. So there's very short representation, very canonical. So. Think of this game for linear combinations. If instead of convex, you have linear combinations, no way, no luck here, right? If I have X in the linear combination, let's say X in the linear space, and I would like to represent it with fewer elements of the basis than it is really, approximately. I don't think we have a good luck there. If you drop basis elements, it could be in the orthogonal direction, so it should not be possible generally. But for convexity, it's true. So convexity really helps. First time I saw this theorem, I couldn't believe it. How can you even not, you don't even need to compute these coefficients. Okay.
And actually lifting this requirement for 1 over k coefficients, does it improve even more, or it doesn't improve?
No, it doesn't improve. No, I think no. I think this actually is the best rate. Well, if you forget the 2, maybe 2 is not a very sharp thing, but I think 1 over root k is the best rate at which the error goes down to 0, even if we allow the weights to be different. Yeah, good question. Yeah. Okay, everything is good. Okay, we have about 10 minutes to do this. So let's do it. The proof. The proof is actually more beautiful than the theorem, and that is the reason I wanted to do this now. The proof is by using probability, by a probabilistic method. Probabilistic method is a term that's commonly used as a way of proving things that are deterministic using probability. So it's a deterministic statement. Nothing there is about probability. Approximate Caratheodory is deterministic, but we will prove it using probability. And this is specifically called the empirical method of Maurey. He's a French mathematician working in Paris. Okay, good. Let's do it. Let's recall first a little bit of standard facts in the probability theory. First fact, definition of the expectation. So if X is a discrete random variable, taking values, let's say xi with probability pi, then its expected value is defined as the sum pi xi. Yeah, familiar definition? Okay, perfect. This is definition. Second, the variance of a random variable is this. Okay, this you should be very familiar with. That's two equivalent definitions of variance. And the new thing that I would like to note, an equivalent definition, one more equivalent definition of the variance is this. You take two independent copies of X. So X prime is an independent copy of X. And that means that this is a random variable that is independent of X, but has the same distribution as X. Think of just flipping another copy of a coin, right? If you have a coin and then just take another coin. So you kind of flip two coins and you consider you compare their outcomes. And that difference of the expected difference of the outcomes, that's a variance. Let's prove this. Proof of this. So let's see. So by the way, guys, is it clear what I mean by X squared now? The independent copy, right? Just the same distribution, independent random variable. Okay, so let's do it. So let's look at the right-hand side and expand it. So what do we have? We have inside, we have X squared minus 2x prime plus X prime squared. Perfect. And then we use linearity of expectation. Now here, as we take the expected value of X prime, we use that they are independent. So expected value factors like this. So that's by independence. And now we use that they are identically distributed. So this thing and this thing, they're actually equal to each other. These random variables have the same distribution and therefore they have the same expectation. And so we have what? Yeah, and this also the same. This is the same as expected value of X squared, which is the same distribution. And this thing, this product is expected value. Let me do it this way. This product is the same expected value of X all squared. So we now simplify this expression, collect similar terms. No?
Ви там одну другу забули поставити.
Oh, yeah. Yeah, this is true. So yeah, we collect the similar term. There are two of these and two of this. Yeah. Two. Okay. 2 of x squared. Yeah, and this is twice times the variance of x because of this definition. Good. Good. Intuitively, all kinds of definitions of the variance measure the same thing, the spread of a random variable. And this is one of the ways to measure the spread of a random variable. You flip the two copies of a random variable and look how different they are. Okay, perfect. And we will need a version of this fact for random vectors in high dimensions. So similarly, if x is now not a random variable, but if x is a random vector, in Rn, the same idea, the same idea of variance holds. So that is a kind of a proxy for a variance. You take x, you take expectation, take the norm, the usual distance. This is usual distance in Rn. And that would be 1/2 expected value of x minus x prime squared, where x prime is an independent copy. This is part of homework 1, to extend the identity that we just proved to random vectors. Good.
What does this? We have norm sign, and we have 2 at the bottom index near the norm sign.
Yes. Okay.
What does this mean?
Yeah. Okay. Yeah. This thing, this 2, right? Okay. Just
Yes.
if you're not used to it, just forget it. This is just the usual distance in Rn, and we put this 2 because it is defined as the sum of the squares of xi, right? The norm, it's just a sum of the squares. And if we change 2 to something else, like to 3, for example, that would be.
Okay, I understand. Thank you.
Yeah, you're welcome. It's just a funny notation for the Euclidean norm, because later we will use different indices there. But if you're not used to it, just forget this is subscript 2, just a distance. I'm glad you asked. Yeah.
But this is a matrix in LP, right? Or something like that.
Yeah, LP, exactly. Here I'll use L2, but generally use LP. I'm not saying this L2 LP now because we have some students who haven't.
Yeah, no problem. Okay.
Perfect. Everything is okay. Everything is good. Yeah, everybody understands what's going on now. For now. Ooh, okay. Okay, perfect. That's our background. Now let's prove the approximate Caratheodory theorem. Back to this approximate Caratheodory theorem. So again, what's the game? Someone gives us t. Someone gives us vector x in the convex hull, and we know, because it is in the convex hull, it is representable as a convex combination. Now, our goal is to find the shortest convex combination possible, the very short one, which is of this form, actually. Okay, so let's do it in a probabilistic way. There will be beautiful proof. So now proof of approximate Caratheodory theorem. So we fix a vector x arbitrarily in convex hull. Since it is a convex hull, we express it as a convex combination from 1 to, I don't know, some number. For now, there is no restriction on the I, zi. It's a convex combination. Like that. And now is the most beautiful thing that you will see today. So we will rethink what that convex combination means in a probabilistic language. Right here, there are some numbers that are non-negative and sum to 1. What in the probability? Exactly. Yeah, these numbers that are greater than 0, sum to 1, they should ring our bell. This looks like probabilities to us. Right? So we can interpret lambda i's as probabilities, and then the sum as expectation. Yeah, expectation of what? Of a discrete random variable that takes, actually random vector, a discrete random vector that takes value zi with probability lambda I. That's a definition of expectation. Beautiful, right? So in this interpretation, yeah, we just set up this interpretation. Let random vector, consider the random vector z that takes value zi with probability lambda I. And what is our equation now? Equation is now x equals expectation of z. So far, so good? X equals expectation of z. Okay. And then we make these copies of z. So we consider, repeat this experiment, consider copies, z1, z2, and so on and so forth. Independent copies of z. And the law of large numbers says that their averages converge to the expectation, which is x. And this happens with probability 1 almost surely. Now this is starting to look exactly as we need. X, we already are representing x approximately as a convex combination of zi's, and each zi's is a random vector that takes value little zi. So is that what we needed, right? That's exactly the approximate Caratheodory theorem, the context of it. We need to represent x as a convex combination of something from T. And this is x, approximately the convex combination of something from, well, what is zi? Zi are from T. So we almost win there, except for now, it is a qualitative statement, and we need a quantitative statement. We need the error, and not just a limit. But making this quantitatively is easy. That's what we do always. We did it last time with Monte Carlo, so we can do this again quantitatively. Let's look at the error. Expected value of x minus 1 over k zi squared. That's the error. That is what I want to control now. And okay, let's see. So maybe I'll bring x inside here. It's expected value of 1 over k zi minus x, like this. I just brought x into the sum because the sum is normalized. It's okay. Good. Well, we know that x is actually the expected value of z, and of each of zi's as well. They're independent copies. So what does it look like really? It looks like we have a sum of independent random vectors. And this is a deviation of zi from its mean. So it looks like we're looking at the variance of a sum only for random vectors. And the variance of the sum is the same. Okay, sorry, let me pull 1 over k out first, just to clear our room for the action. Okay, because of the square, it pulls with the square. Then we have zi minus expected value of zi. Square, okay. Okay, so what does it look like? It looks like variance. So variance of a sum. And we're claiming this is the same as the sum of variances. Okay, expected value of zi minus that. Variance of a sum of independent random variables. Random variables equals the sum of variances. But for random vectors, it's also true, and this is homework 1 as well. This is one of the problems in the homework to extend this fact for random vectors.
Maybe small, I forgot the English word. Okay, we have at the top of the screen, x equals sum, yeah, and we have here zi having this sum. And later we have also zi where we have LLN. Do I understand right that these are different zi's in different meaning? First is all values then that z can have, and second is different not values of z but different copies of z. Yes.
Mm-hmm. Yes, Matej, exactly. And I may
okay, just to be sure that I'm
yes.
right.
It's it's a good question, and we should have emphasized that. So first of all, we set up the distribution for later, and the distribution involves different vectors. We call them zi's. So we take random vector z, and it set up the distribution. It takes, let's say, 10 values: z1, z2, z3, z10. Now, as we set the distribution, now we make different copies of that random vector. Capital Z1, capital Z2, capital Z3, capital Z11, and so on and so forth. And this meaning, maybe to differentiate between these two meanings, I should have chosen a different notation here. Z, instead of I, let's take index J. Of course, it doesn't change the mathematical meaning of it, but it emphasizes that these are different things, capital Z's.
Okay, thanks.
Yeah, you're welcome. Thank you for asking this. It's a good way to clarify things. Yeah, everybody is okay with the last expression here? Yeah, think of this, if this was for random variables, and you just have this parentheses here, that will be exactly this: the variance of the sum equals the sum of variances. That's it. Right. And now we have the random vectors. Okay, that's homework. Okay, perfect. Let's see. So what do we have here? This expression. Okay, all of these, they are identically distributed. So it doesn't even matter which term. All these terms are the same. That's because it's an identical distribution. Identical distribution. And so, okay, there's a crux of the proof. We have 1 over k squared in front. We have k terms in the sum, and each term equals this. Yeah. And we can, so this is 1 over k times, and then we use the alternative definition, whatever, the identity for the variance, this one. So the variance equals 1/2 expected value of the dispersion between x and x prime. So I'll use it here. So it's k times 1/2, and then there is a dispersion of z minus z prime like this. This is from fact 3. Okay, we're almost there. Just one last thing to note is that both, so what's z and what's z prime? Z takes values zi, and these values are in t. So z always takes value in t. This is in t, this is in t. So the difference is less than the diameter of t. Because the diameter is defined this way. So it's the largest difference, largest distance between the 2 points. And the diameter of t by scaling, we assume this to be 1. We assume that this is less than 1. So that's it. It's less than 1 over 2k, because we take expected value of 1, and that's it. So we proved that expected value of something is less than 2k. And if the expectation is less than 2k, then the random variable whose expectation is less than this, of course, it takes some value that's less than that. Right? If we have a random variable whose expectation is less than 10, then it must take that value less than 10, otherwise the expectation is larger. So there is a, we call it, there is a realization of the random variables z1 such that this expression is less than its expectation, less than 2k. And the zi's, remember, they're on t, they're in this convex set t. So that's it. Quad arid demonstrandum. So there exist points in T that makes this approximate convex combination. And we proved the approximate Caratheodory. Any confusion? Is the last step also clear? How we went from the probability statement to deterministic statement? Yeah, probability statement again is expected value is less than, let's say, 10. Therefore, there exists a realization, it's value from the variable that's less than 10. That's what we.
So can I ask just to be sure, like?
Yes, Matej.
It turns out that not only we can choose points with like the same weights, but those points are from the initial representation set, but with the same weights. Yeah.
Yes, I'm not sure if this adds any generality to the statement though, but yes. So we could have. Let me think. Yeah, in fact, we could have forgot, like, let's state the Caratheodory theorem differently. You just forget T, there's no T anymore, right? So you just give me some convex combination like this, and my job is to make a better convex combination, approximately, right? So I can promise you that I can shorten this length to something that doesn't depend on the dimension, and also to make all the weights equal to each other. Yeah, so that's exactly what we did in this proof. Right. So we took a specific convex combination and we made it better.
Yeah, and so the second question, if it would be allowed to like take not the same weights but different weights, it may be the case that we can like make this error smaller if we use different weights.
Okay. Okay, Matej, good question. There is something I need to tell you
That
about.
was not Matej, it was Evgeny.
Yeah, same. Oh, sorry.
That
That was
doesn't
Evgeny.
matter.
Ah, sorry, Evgeny. I don't see all of the participants as they speak. So, Evgeny, it is not okay. So, I need to tell you something. Although in the approximate Caratheodory theorem, we take this, the xi appear as they're different. We never insisted that they are different. Right? Nobody forbids us to repeat the same xi multiple times in this combination. And that can happen. In the proof, it actually happens. The proof never, these zi's could repeat themselves. Their values could repeat. So the proof doesn't forbid that. Now, so we allow xi's to repeat. And this we can use to create the same weights out of different weights by repetition. So for example, if one weight was 2/3 and the other weight was 1/3, how do I make it the same? I just split 2/3 in 1/3, 1/3, and 1/3. So so let's say we had 2/3 Z1 plus 1/3 Z2. And I am making this 1/3 Z1 plus 1/3 Z1 plus 1/3 Z2. I made all the same weights, the same expression, which means that we can do this trick. We can repeat for practically any combination. Which means that the answer to your question is no. Nothing is getting better if you allow different weights. Because if you allow different weights, I can make the same weights out of them by splitting. Of course, the numbers need to be rational, but it's an approximate result, so I can always approximate a real by rational number. That should not be a problem.
Yeah, I got it. And if we allow repetition of this ci, it may be the case that in this result set of points which we use to represent x, there are some repetitions like z1 and z2 in this representation, so weights actually are not equal even at the beginning. Yeah, okay, got it.
Yeah, exactly. Yeah, I don't think the results would actually, I don't know. If we disallow the repetitions, disallow the repetitions, can we hope for something like this? Actually, I don't know. Yeah, think about it, guys. I don't know. If you disallow the repetitions, if you insist in the approximate Caratheodory theorem, if you insist that all of the xi's be different, can we still have that result? I'm not so sure. Maybe not. It's a fun question.
But they come from the convex hull, which is usually like dense, in the meaning that the difference does not matter much because you can pick something really, really close.
No, xi's come from T, not from the convex hull, right? Xi's themselves.
Oh, right. Okay, and it can be discrete. Okay.
Yeah, for T could be very discrete. Could just a bunch of points somewhere. Yeah. Yeah, if it was for convex, I could just make it a little different. But no, they come from T. So yeah, that's a good question. Anything else? Any other questions?
So this last step where we move from expectation to the realization, it actually doesn't feel like this bound. Like the feeling is that this is not very precise, because if the expectation is less than something and we choose the realization, it's usually half of the probabilistic weight should be below. So kind of it kind of feels that we can find something even lower. But you mentioned earlier that this is the precise bound. So maybe.
Yeah, Pavlo. Yeah. So, but let me clarify. What I know, I don't know, 90% sure. I think I know that the rate is precise. So you cannot improve the rate 1 over root k. I'm not sure about the number 2 here. Maybe it's not precise. And that trick where you say, well, the expectation is less than this level, therefore I can find realization, let's say, twice lower. Well, I'll buy that you can get yourself like a better factor of 2, but you can never get yourself a better rate as it goes. So it could be an improvement by a constant probably, but not, I'm not sure. Actually, wait a second. Okay, no, I'm now less sure about that as well, that you can improve.
So I think there are some kind of certain family of distributions where you cannot improve much, but for kind of good distributions, maybe I don't know. It just feels that it's like this step is covering a lot of distance.
It could, I agree. Normally, my instinct, like gut instinct, is that you would not be able to get much of it, because as k goes to infinity, usually there is the phenomenon that we'll study. It's called concentration of measure, that random variables tends to concentrate tightly around their expectation. So they tend to take most of their values very, very close to their expectation. And that is almost a universal phenomenon, so which makes me kind of pessimistic about the possibility of going significantly below expectation in this case. Although we're not asking for too much, we just need one value. We just need, does there exist a value? We don't need a lot of measure there. So I don't know. Yeah, it's a good question. I don't think anybody knows what's the optimal constant here in 2. I think 2 is maybe optimal, but I'm not sure. Yeah. One other question you can ask, and this is, okay, we're still on record, but one other question we can ask about this is a randomized algorithm. This gives you a pretty good randomized algorithm for shortening convex combinations, right? Which is sample, just set up this Z and sample, and that's it. It's a very fast algorithm. But is there a deterministic algorithm? Right? Equivalently, in mathematics, you can say, okay, this was an existential proof. We just proved that there exists a combination, but you never really found one. Is there a formula? Can you just write down the formula instead of saying it exists? And I believe this is one of the rare cases where it is possible. Actually, there is the deterministic approximate Caratheodory theorem. There's a greedy method. Yeah, I believe that's actually very, very simple to describe. It's a greedy algorithm. Greedy in the sense that you start building your convex combination from the element that gives you the best improvement, the most of the improvement. Like you're trying to build your convex combination, and you're thinking, okay, which of the xi's I should choose the first, x1, x2, x3, or x4? Well, I choose the one that approximates x the best. So that x minus something times x1 is the best, gives me the better error. And then I just proceed in this way. I look at the residual and then I approximate the residual and so on and so forth. So this greedy method is probably doing the job there. It's a little hard to prove though, but yeah, this proof is the best in some sense of elegance, I think. Speed. Stop recording now.